I've just realized that people can't unmute themselves. That's why Brendan isn't saying hi.
Oh. Okay, are we ready?
Yes, I am ready. I'm just waiting for you. Yeah.
Okay, wonderful.
Yes.
Well, welcome everybody to this month's MCAT seminar. Thanks to the Topos Institute for hosting us, and thanks to everyone involved for all the technical things, and thanks for coming. Today's talk will be by Minani Iragi of the University of South Africa, and he will be talking about categorical approaches to quasi-uniformity. I think that's your title. So I will stop sharing that, and thanks.
Okay, so so I need to reshare now, I think.
While you're doing that, I will just remind everyone that if you would like to ask questions, then please feel free to type into the chat just to me, Eugenia Cheng, and then at the end of each section, I will ask Minani if there are any things that need clarifying. So anything that's clarifying that part of the talk, I'll then pose from the chat, and then everything else we'll do at the end in question and answer time. Thanks.
So can I start?
Yes.
Okay. Yeah, thank you very much to the organizers of this seminar for giving me this wonderful opportunity to speak here today. And I would also like to thank Eugenia, with whom we spend much time discussing the slides for this presentation. So thank you very much. I will now start by giving you an overview of my talk. So basically, what I will be doing is to show you how to do topology into category. So remember that we usually define a topology on a set using open sets, but this can equivalently be described using a closed sets. And classically, we think of closing subsets under limits. So an abstract formulation of this gives us on the category of topological spaces what we call a closure operator. And what is good with this closure operator is that it also allows to have an abstract formulation of continuous maps. At this point, one can now think of replacing the category of topological spaces with a quite nice category so that topological concepts and notions can be described and studied in an abstract category. So this method of moving from the category of topological spaces to an abstract category is often what we call doing topology into category. It's quite a very powerful tool because it allows us to apply topologically motivated ideas to categories outside topology. So, and if you look at it, it sounds cool. It sounds as if it's easy to move from topology to abstract category, but it's not, because extending a concept from a classical setting to a categorical setting requires first a good understanding of this notion in topology and a better understanding of categorical constructions, which allows you to put it into a right categorical setting so that the classical concept appears as a special case with more understanding and more applications. So in my talk here, I will be looking at how to do to study quasi-uniform structures on categories. And these structures, in fact, they allow to study things like uniform continuity, uniform convergence. So this is basically what I will be doing. So let me now give you the structure of my talk. As I'm studying quasi-uniform structures on categories, I will first start by telling you what is a quasi-uniform structure on a set, where it comes from, what is the idea of a quasi-uniform structure. After that, once we understand it, we will now need to know what is really needed to do topology into category. What are the tools that are important to do topology into category? And once we have those tools, we can now define a notion of quasi-uniform structure on a category. Once we've defined it, we will now go to focus on our main result in the talk. And this main result basically shows us how do you construct a quasi-uniform structure determined by a subclass of M. And once we've given our results, we will now go to look at the whole list of results that our main result allows us to prove. This is basically what I will be doing in the talk. So I will now go to the first section, and this is a quasi-uniform structure on a set. We want to understand what does this notion comes from. And for us to really see where it comes from, let me start by saying that quasi-uniform structures are like uniform structures missing one condition, that is a symmetry condition. We will understand later what it means. So I will remind everybody what is a continuous function at a point on a subset of the real line. And on the other hand, I will also remind what is a uniformly continuous function. These two will lead us into understanding where the notion of uniform structure comes from. And from uniform structure, we will go to the quasi-uniform structure. Okay, so now, a continuous function, basically the continuity, is described using neighborhoods of a point, because we want to define continuity at a point. And this is really about the neighborhood of a point. On the real line, with this notion, you can be able to describe open balls. And a collection of all these open balls, depending on a positive real number delta, gives us what we call a base of a topology on the real line. And this topology is often called the topology of the real line. Remember that continuity here, it's about a neighborhood of a point. On the other hand, we can describe what we call quasi-uniformly continuous function. this is no longer about a neighborhood of a point. It's now about 2 points, x and y varying together, which means where we had to use a neighborhood to define open balls, we no longer have neighborhood of a point, but we have the neighborhood of the diagonal. The d delta is the neighborhood of a diagonal. And if we take the collection of these d deltas, what we get is in fact a base of a uniform structure on the real line. And here we will be thinking of this d as relations. But as you see, the absolute value makes it symmetric. But in what follows, we will drop the symmetry condition to define a quasi-uniformity. So with these classical notions that we've reminded, we can easily go to the quasi-uniformity, because it gives us an idea that you want to define a quasi-uniform structure, you must have a collection of relations, and these relations, in fact, they are neighborhoods of the diagonal. It is this collection that gives us what you call a quasi-uniform structure. Now, I'm going to the definition. What is really a quasi-uniform structure on a set? Remember now, you have a set, you take the collection of relations on this set, and each of this relation must first be reflexive. We must have a condition that we call U2. This is the one related to the triangle inequality. It means you have a relation in there, you can find another relation D dash, such as that when you compose D dash by itself, you get a relation which is contained in D. And the third axiom is upwards closed. Upwards closed. It means you have a relation in there, and there is another. If there is another relation V which contains this first one, and V must also be a member. And the last one is finite intersection. So when you intersect the finite members of this collection, you must again get a member of this collection. This is really what we will be calling a quasi-uniformity. We should maybe keep in mind the axioms in terms of reflexivity being related to the triangle inequality, the upwards closed, and the finite intersections, because this is how we will be referring to them to try to remember what they are. I need also to say that unions are automatically there from axiom 3. So if you have union members, the union of members of this collection is also a member. Now, in most cases, we shall be describing a quasi-uniformity on a set by defining a base for this quasi-uniformity. And the base will be a collection of relations satisfying 3 axioms. It will only not satisfy the upwards closed. That is what we'll be calling a base. And the base will be quite very useful. Now, the point is, we want to know, because a part of the quasi-uniform structure, we know also the topology. We want now to understand what is the relation between the two. And if you remember what we know from a metric space, every time you have a metric space, you can get a topology induced by that metric space. And the way you get it is that an open set in that topology, it's the one with a property that every time you get a point in that set, you can find an open ball centered at that point, and which is contained in the set. And we want to use this idea to define a quasi-uniform topology induced by a quasi-uniformity. Really what we do is to say, you have a quasi-uniformity on a set, you take the collection of all the subsets of this set with the property that every time you take a point in that set, the uniform neighborhood of this point is a subset of the set A. So you could think of this uniform neighborhood as what we saw before, or the real line. And if you use a metric space, this is really an open ball centered at this point. So this is what we call. So from here, we know that you have a quasi-uniformity on a set, you can make a topology on this set. And what the question we can ask is now, what happens in the other way around? Can we also start with a topology and make a quasi-uniformity? And this is where we want to go. If you have a topology which is equal to a topology induced by a quasi-uniformity, we say that this quasi-uniformity admits is compatible with a topology, or equivalently that the topology admits this quasi-uniformity. So if you think of the quasi-uniformity we saw earlier on, you will see that the topology of the real line is exactly the one induced by our quasi-uniformity on the real line that we started with in our previous slides. Now, quasi-uniformities are quite nice because the good news is that for every topology, you can find a quasi-uniformity which generates it. And this is good because it does not happen for uniformities. For uniformities, only completely regular spaces admit a uniform structure, which means quasi-uniform structures are good because you can go from quasi-uniformities to topologies and back. And really, a lot of authors, they just view quasi-uniform structures as an alternative approach to the study of topological spaces. This is in fact one of our interests in trying now to understand what happens to this nice relation between quasi-uniformity and topology in a category. That's what we really want to understand. What does it become? So again, to remind, we know now you can go from quasi-uniformity to topology. You can also go from topology to quasi-uniformity. That is always possible. Okay, perfect. Now, remember that our point here is to really study quasi-uniform structures in categories. And us, we are interested in defining quasi-uniform structures using maps so that we can treat them categorically. And what we do is that we want to go from the definition of a quasi-uniformity as a collection of relations to the definition as a family of maps from the set to its power set. And how do we do it? You map each point to its uniform neighborhood. It helps you to make maps from the set to its power set. And now what we only need to see, what do our four properties become, the four axioms. So what does the reflexivity becomes? What does the axiom related to the rectangle inequality becomes? So, and clearly we'll see that reflexivity will just mean every time you take a point, it must be in the uniform neighborhood for each member that you take in the collection. And we can equivalently reformulate the axiom related to the triangle inequality, the upwards closed, and the finite intersections. But now, if you look at how we obtain the maps, it's mapping a set to its power set, which means because these are uniform neighborhood, we can also map the set to the union of uniform neighborhoods for each point in the set. And this indeed allows us to extend this family of maps from the set to its power set to a family of Indo maps on the power sets. And our next slide really clarifies this. The maps, you take them, you get them by mapping every point to its uniform neighborhood. For any members that you take in the quasi-uniformity, you can extend this to Indo maps on the power set as just mapping the subset to the union of neighborhoods for each point that you take in A. This is really very good news because the quasi-uniformity, which was a family of relations on the set, we are able to view it as a family of Indo maps on the power set. The only question now is, how do we treat power sets in a general category? Because we need to know how to treat them so that we can be able to define the quasi-uniformity in the general category. We need to be able to do that. And the second, this is good because we will also need images, and the images because apart of just the four axioms, we have also continuity. We need to be able also to express continuity and uniform continuity somehow. So the tool, the categorical tool that allows us to obtain this is a factorization system. So to just remind everyone about this idea, this will come in our next slide. But as I am at the end of my first section, I would like to know if there is any question, if there is something that must be clarified in this first section before moving to the next one?
There don't seem to be any questions at the moment. Thank you.
Okay, perfect. So we're going to the next section. This is now, what do we really need to be now able to define this quasi-uniformity in a category? Because we have understood it on the set. How do we do it in a general category? As a question. So to answer that, let me start again by reminding everyone the idea of factorization system from a situation that we all know from sets, hopefully. We know that subsets can just be viewed like monics, and also each function can be factored through its image, which means you can compose it into an epic monic and have what we call epic monic factorization. And another good news is that, because you remember we need to know how to treat power sets. Power sets, they are complete lattices with the union and intersections. And another good information is that for every function that you take, you have an image pre-image adjunction in the power set. This also will be very important. To just fix the ideas, we want to have a category where these elements can work so that we can be able to formulate the notion of quasi-uniform structure. Now, if you look, we say we need a category C. Think of having, for example, our category of sets with the image pre-image with epic monic factorization. Here we will need the category C with the NIM factorization. And for each object in the category, we can define sub-objects. Remember, we want to treat subsets, power sets into a category. We need a notion that replaces power sets. And these are this is a sub-X. Sub-X is just the collection of all those morphisms in M with codomain X. Think of subsets being seen as monics. Okay, so we can also order this in a very natural way. But another question is, power sets are complete lattices. We want to make sure also that our sub-X is M complete. And that's the next question. How do you make sure that it's a complete lattice? And the notion that allows us to make it a complete lattice is what we call the M-completeness. And M-completeness is just a technical condition that makes sure that we can generalize the arbitrary intersection. This condition includes wide pullbacks. So, which means if our category is M-complete, then sub-X is a complete lattice for each object that we take in the category, and with the greatest element being the identity morphism on the object. Now, this is also a very good news, because we are now able to also have the image pre-image adjunction for each morphism. In mind, if you come back, you will see that we are now able to treat power sets. We are now able to treat image pre-image adjunction for each morphism, and we are also able to make sure that sub-X is a complete lattice, which is really what we need for us to be able to define. It's a good news that we now have everything we need to define a quasi-uniformity on a category. But to really make sure that we understand how do we move from the category of topological spaces to the abstract category C, I have made a small table. And this table has got two kinds of tools. We have tools that we use in top, and we want to know what do these tools become when we are by the side of an arbitrary category C, so that we can be able to see how do we move from top to an arbitrary category C. The first tool that we said is that subsets. We use subsets to define a topology. We use power sets. And when we are in the category, this becomes the sub-objects. And remember that our sub-X, our power set is the one which becomes the sub-X. And it's a complete lattice, we have said. And being a complete lattice, it can be also viewed as a small category. Okay, now we want to know what do endomaps on the power set becomes, because as we need these endomaps, if you remember very well, our quasi-uniformity, we were able to express it as a family as a suitable family of endomaps on the power set. So because sub X is a category, now endomaps on sub X becomes the functors, and the collection of those endomaps becomes a functor category on the sub X. These tools are very important. On the other hand, we said U will be smaller than or equal to V if the uniform neighborhood of X is a subset of the uniform neighborhood of X will be for every X that you take in the set. Now here we don't work with elements, we work with sub-objects. So saying U is smaller than or equal to V will now be that U of M will always be smaller than V of M for any objects that you take. Now what is left is that we have our 4 axioms. These 4 axioms, we will now formulate them using a categorical language. And another thing is that we have continuous maps. And on this side, we need to make sure that there is continuity with respect to the structure. And our uniform continuity will just be called the U continuity, where U is a uniform structure that we want to define. This is now very perfect because we have tools. We know that tools in top, what do they become in a arbitrary category C, so that we can be able to work here in this arbitrary category. And this is the end of my second section, which basically deals with tools that are needed to do topology into category. So again, before I move to the next section, I will I would like to ask if there is any question so that I can answer it before we move to the next section.
Thank you. Yes, there is a question, which is why do you want a complete lattice?
Okay, in fact, the reasons why we want a complete lattice, because we need these arbitrary intersections, because we will need them to construct our quasi-uniformities. We will need collections that are closed under arbitrary intersections. So we need to make sure that these intersections, they do exist. That's why we make the condition which makes them to exist, which makes the subsets to be a complete lattice. Perhaps it will also become clear a bit later when we use them for defining our quasi-uniformity on C.
Thanks, that was all the questions. Oh, wait. Okay, yeah, that's all. Thanks.
All right, thank you. Let us now go, because we have the tools. So what we can now do is just to present the definition. What does it become? So we remember that collection of endomaps on the power set, they become now an endofunctor category on sub X, and the quasi-uniformity will just be a full subcategory of that functor category, satisfying first axioms 1 to 4 that we formulate categorically, and plus the axiom 5, which is a U continuity. Because remember, we are replacing the category of topological spaces with a nice category C. And here in the top, every morphism is a continuous map. So we need to make sure here that every morphism in C is continuous with respect to the structure. And for the quasi-uniformity, this axiom 5, we often call it the U continuity. So this gives us an idea. This is what reflexivity becomes, our upwards closed, the axiom related to the triangular inequality, as well as our finite intersection. And every time we say that U is a quasi-uniformity in a category C, we shall mean what is said in this definition. And it's very good because this is our basic. It's from here that we will be doing the rest of our talk. Perfect. Now, once we have this definition, I would also like to remind you something. You remember that on sets, we said you can move from quasi-uniformity to topology. You can also move from topology to quasi-uniformity. Now, inside the category, we work with closure operators and quasi-uniformity. We will also need to know how do we move from quasi-uniformity to closure, and if there are ways to move from closure to quasi-uniformities. For this reason, we define the whole large collection of all quasi-uniformities on C that we call QCM, because we will want to define monotone maps from this collection of quasi-uniformities to the collection of closure operators that we will define later. And this collection can thus be ordered by saying that U is smaller than or equal to V if every time you take a member of U, you can find a member of V which is closer than the member taken in U. This will mean that U is smaller than or equal to V. U and V are quasi-uniform structures on C. Now, again, you remember earlier on, we defined what is a base on a set. We now need to know also what as a base for a quasi-uniform structure becomes on the category. And once we've seen our definition, we will see that we will require all the other axioms except the upwards closed. The base is very important because in most of the time, to describe a quasi-uniformity, we just define a base for it. Perfect. Once we've seen that, we can now see, because our aim is to say, how do you study the relationship between topologies and quasi-uniform structures in category? Before doing that, let's see how these two relate first on the category of topological spaces. How does it relate? The first we've seen it, every time you have a quasi-uniformity, you can induce a topology. And there is a good news that every time you have a topology on a set, you can find a number of quasi-uniformities which generates this topology. So there is one way of moving from quasi-uniformity to topologies, but you have multiple ways of coming back, of moving from topologies to quasi-uniformities. Now, the next is that the collection of all quasi-uniformities on top is a complete lattice. The same works also for closure operators. It's also a complete lattice. So in top, we are able to move from quasi-uniformities to topologies, indeed, to closure operators. Indeed, we can have monotone maps from the collection of all quasi-uniformities to the collection of all closure operators on top. We need perhaps here to mention something very important. We know that in top, you can move from all the notions that you describe using closure operators, you can equivalently describe them using interior operators. So in top, it's also possible to use interior operators. But later when we work on a category, we will see that interior operators do not behave well. So that's why we mostly use closure operators on abstract categories. So our main theorem will really focus on describing monotone maps between as uniform structures and closure operators on a category. And again, I am at the end of my paragraph, and I would like to ask if there is any question. Remember, in this paragraph, what we've done is to define a quasi-uniform structure on a category, define the lattice, the large collection of quasi-uniform structures on C, and define the base for a quasi-uniformities, for a quasi-uniformity on C, and again remind how do quasi-uniformities and closure operators relate on the category of topological spaces. So if there is any question, I would like to answer it before we move forward.
There are no questions at this point. Thank you.
Okay, all right. So now we are ready to go to our main result. Again, before we give the main result, let's go again to tools. First, on one side, we have the tools that we use in top to discuss result. And we want to know what again they become in the category, in a category C, so that we can be able to understand where does the result come from and what does it lead to? Why do we need it? Okay? So the first thing that in top, we use embeddings. When I say embeddings, I mean that if you remember our factorization system, we have our class M, which is the class of embeddings, and we have our class E, which is the class of surjective continuous maps. On the other side, where we have embeddings, we just have the class M. In top, we use closed embeddings. On here, we will fix a subclass N of M. Now, here, for any topological space, we consider as a closed subset. On the other side, for any object in C, we take those sub-objects in M with codomain X. By this side, we have pre-images. On the side of a category C, we use pullbacks. But in top, we know also that the pre-image of a closed subset is closed. Here we will require that the class N is closed under pullbacks. So that it means every time you have the inverse image of a sub-object is in N, it's also a sub-object of N. So these tools are very important. They are not finished. Let's go to the next. For all sub-objects that you take in top, you can consider Nx of all sub-objects of S. Here we consider Nx of all morphisms in N with codomain X. Now here that we know that arbitrary intersections or intersection of closed subsets is closed. On this side of the category, we will require that our class Nx is closed under arbitrary intersection. And we remember, we can now see why we wanted this intersection to exist, so that we can work on tools that we know that they are there. Because earlier on, someone wanted to know why do we need sub-X to be a complete lattice. So once you have this class of closed subsets, you can build a relation on each subset of this class. Because remember, on this side on top, we use relations to describe a quasi-uniformity. But on this side, instead of relations, we must build monotone maps that we denote UL for each subclass of N. And with those, we can take those collections of relations on this side to make a quasi-uniformity on top, while on an arbitrary category C, we take a collection of those monotone maps. If you remember, it's a full subcategory of the end-of-functor category on sub-X, which makes a quasi-uniformity. So these are the tools that we really need. From now, we see how we do from top to an arbitrary category, so that we can try to get the idea, where do all those notations come from? So next, we are now able to have our main result. If you look on our tools, what you do, you take a subclass of M, close the under formation of pullbacks. We understood why we need pullbacks and how we do it from top to C. Now, for any C, you can make that Nx. Remember, our Nx is a collection of all those sub-objects in N with codomain X. And this must be closed under arbitrary intersections. We've seen why. And now you can consider that subclass, that collection of all subclasses of N and X closed under arbitrary intersection. Once you've done that, you now make a monotone map for each subclass. And once you've made a monotone map for each of subclass L of Nx closed under arbitrary intersection, you can now take the collection of all those maps, monotone maps, and make a base of a quasi-uniformity. And this quasi-uniformity is the one we call quasi-uniformity determined by a subclass of N, which means from here, you take a subclass of N closed under pullbacks, you are able to make a quasi-uniformity which is determined by this class. In fact, this is our main result. And all the other results will just be deduced from this. Perfect. We have our main result. Now, we need to move to a very important notion. We've seen in top that you can establish a relation between quasi-uniform structures on top and closure operators. In fact, you have one way of moving from quasi-uniformity to closure operators, but you have multiple ways of moving from closure operators to quasi-uniformities. We want now to have also an abstract formulation of quasi-uniform structure of a closure operator on a category C. The closure operator is also a family of endomaps. Here you think of having the category of quasi-uniform structure. You remember there, you take every subset, you map it to its closure, which means the closure operator is, in our understanding in top, a a family of maps, window maps on the power set. But we saw that in the narrowity category, we don't use power sets, we use sub X. And because we know that the subset is always smaller than its closure, we require that the subset, the sub-object will always be smaller than the closure. And every time the sub-object is less than or equal to another sub-object n, the same will happen for the closure. And because we know that the closure operator on top allows to give an abstract formulation of continuous maps, we can do that for an arbitrary C, and why we are able to get what we call a closure operator on a category C. Now, again, because we will need to know how to move from closure to quasi-uniformities and back, we will note by CLCM the collection of all closure operators on C with respect to M. But here, something very important is that we have closure operators with the property that every time you take the closure of that sub-object, you get the same sub-object. And this closure are called the idempotent closure operators. Have in mind the Krutowski closure. If you take the closure of a subset, you get the closure of the same subset. So this is in fact the ideas that we are trying to bring here. So now we know what is a closure operator on a category. We are able to say, you have a quasi-uniformity on a category. How do you also make a closure operator? Because you have in mind, every time you have a quasi-uniformity on a set, you can have a topology. So here you have a quasi-uniformity, you can make a closure operator by taking the mean of all the members for each sub-object in X. And the notion that we saw on sets, we saw that if you have a topology which is equal to the topology induced by a quasi-uniformity, we say that this quasi-uniformity is compatible with the topology. Also here we want to say, if you have a quasi-uniformity with a closure operator, which is equal to the one induced by a quasi-uniformity on a category, you say that this quasi-uniformity is compatible with a closure operator. Or equivalently here, you can say that the closure operator is generated by this quasi-uniformity. This will be important because it will help us to know how do you move from quasi-uniformities on C to closure operators. And we have seen previously how do you move from closure operators to quasi-uniformities. Perfect. Now, we have those two. The next is, we want to get something very important from our previous result. We want to ask, you have a closure operator, which is idempotent. Can you construct a quasi-uniformity which generates this closure? As we saw that, you can start with the topology, you make a quasi-uniformity, which gives you back this closure. And we saw that there are multiple ways of doing it. We wanted to prove in general that if you have an idempotent closure operator, you are able to construct a quasi-uniformity which gives you back this closure. And the way to do it is to use the tools that we saw before. We have seen, you take a subclass of N closed under pullbacks, you can make a quasi-uniformity which is determined by this class. So what we need to have just here, we call that class N the class of closed elements of M. So that for each object that you take in C, our NX becomes now the class of closed sub-object of X. Remember that a sub-object is closed if it's equal to its closure. Like what you say in sets, a subset is closed if it's equal to its closure. So you can also do it here using sub-objects. And NX is closed under with intersections because our with intersections of closed sub-object is also C-closed. And something important, you can now build the monotone map for each subclass L of N. And this monotone map is in fact a closure operator because we've seen closure operator as a closure operator on C is a family of window maps on sub X, which is grounded and it's monotone with the continuity condition. If you take the collection of all those closure operators, you make in fact a quasi-uniformity. And indeed, the closure operator induced by this quasi-uniformity is exactly the closure operator C. So this is quite very important because it now says you have the closure operator, you can make a whole family of closure operators, such as that if you take the meat of all the closure operators in this family, you get back what you started with, which is really what we know, that the quasi-uniformity on a category can be just characterized as a family of closure operators. So this is very good. If you remember what we saw earlier, we said that in top, you are able to move from closure to interior and back. That is facilitated because our power sets are Boolean. You can use complements to move between closure and interior. But here in top, it's no longer possible. We are able to define interior operators, but you no longer move from closure to interior because sub-X are not always Boolean. So that's why interior operators, things do not work well like a closure. So we prefer to use closure operators because of its good behavior on categories. Now, I am at the end of my paragraph again. Let me remind you, what we've shown in this paragraph is that you, for every subclass of n closed under pullbacks, you can make a quasi-uniformity which determines it. We've shown that you depart with an idempotent closure operator, you can make a quasi-uniformity which generates this closure. Those are the two main results we've proved in this section. So I would be glad to know if there is any question that I can answer before we go to the last section.
There don't seem to be any questions at the moment. Thank you.
Okay, perfect. So we keep going. Now, the next section is, we've seen our main result. We want to know now, what can we prove from our main result? So this is our next section. If you look on our main result, really, it says you take a class, a subclass of n closed under pullbacks, you make a quasi-uniformity, which determines this class, which means it gives us a way of moving from the collection of subclasses of m closed under pullbacks to the large collection of quasi-uniformities. And the first result we can prove there is that there is a Galois connection between the large collection of quasi-uniform structures on C and the subclasses of M closed under pullbacks. This can be proved. Another very important result is that the quasi-uniformity has been a structure that many authors have been studying, because every time you have a quasi-uniformity, a topology, you are sure that you can find quite a number of quasi-uniform structures which generates this topology. Another result is that our main result allows us to describe all the quasi-uniform structures compatible with the closure. We are able to do that. The third is that from our main results, we can also be able to describe subcategories determined by quasi-uniform structures. And how do we do it? The way we do it is that every time you have a full subcategory, you can show that it induces a quasi-uniformity. And this gives us, again, a way of moving from the collection of subcategories of C to the collection of quasi-uniform structures. This also makes a Galois connection between quasi-uniform structures on C and full subcategories of C. And again, we can, as we've seen, our aim is to be able to apply topologically motivated ideas to categories outside the topology. We are also able to apply this to many examples, including groups, rings, topological groups, for example. To just mention one of them, I can show you how we do it for groups. Remember we said, what do? You take C, you make a subclass of n closed under pullbacks. And with this class, you make a quasi-uniformity. And this quasi-uniformity is determined by this class. So let's take the category of groups, with M being the injective subgroups, and fix our n to be the class of injective normal subgroups. Remember that normal group homomorphisms are those group homomorphisms with the property that the image of the morphism is a normal subgroup in the codomain. So we take N to be the injective normal group homomorphisms. And the good news is that this class is closed under Hilbert's. Now, if you look what an injective normal group homomorphism is, it says if you take any group, NG gives now all those normal subgroups of T, because we know that arbitrary intersections of normal subgroups is a normal subgroup. It tells that the class NG is closed under arbitrary intersections. And what we can now only do is to take each subclass of these normals, this class of normal subgroups, build a monotone map, which is in fact a closure operator, and take the collection of all of them and make a quasi-uniformity. And here, this quasi-uniformity, as we've seen in one of the main results, is just a family of idempotent closure operators on the category of topological groups determined by the class of injective normal subgroup. Now, I'm towards the end. I would like to say that the work is really at the start. Our aim have been not only to just study quasi-uniform structures on categories, define them, and understand how they relate to closure operators, but we want to study main properties like a completion. How do we now study completion of objects in a category using quasi-uniform structure? This remains our long-term goal, and we are sure that with a pace of progress, we will be able to do it sooner than later. And again, we know that in function spaces, we can also define quasi-uniform structures and study what we call quasi-uniform convergence topologies on function spaces. We want to know, once we've defined a quasi-uniform structure on a category, how do we now describe quasi-uniform convergence topology? Our aim is also to do that, to make sure that we are able to describe basic concepts that led to the definition of the notion of uniform structure. Now, for someone interested, I have mentioned some of our recently published papers. It can give you more understanding on quasi-uniform structures and closure operators on categories, and this can be freely found from topology and its applications, applied categorical structures, and so forth. I really would like to thank everyone for taking your time to listen to my talk. And again, once more, thanks to Eugenia for making everything possible. Thank you.
Well, thank you very much, Minani, for that very clear and interesting talk. So now, if anyone would like to ask any questions, please feel free to type them in the chat just to me, and then I will pose them. And so we do have a question. And the question is, if we take the example of the category of groups, do we get the usual notion of a topological group? And so also, what happens if we take the category of topological groups, and how should we think of that?
Okay. So for the first question of the category of groups, I'm not really sure about that, because the aim of having that example is because we know the closure operator on the category of groups, and our understanding of quasi-uniformity as a family of closure operators, we are able to ask which class gives us such a family of idempotent closure operators. But I haven't asked myself the question whether it allows to get the notion of topological group. That's for the first one. For the second, on topological group, it's true. if we, the notion of uniformity on topological groups is just an example of quasi-uniformity on a category. And in one of our papers, it's mentioned as an example. You just always map X to the neighborhood, and you get really the notion of uniformity on topological group. So that's what I can say.
Thank you. Okay, we have another question. This
Yes.
work is about categorification of topology, right?
Mhm.
So
Yes.
can you abstract some general principles from the examples you've dealt with?
I don't even know. I don't understand what he means by categorification of topological spaces. Probably that I'm not aware what it does.
Would you like to clarify in the chat, the person who asked this question?
Yeah, probably if he can clarify the question.
So are there some general theorems that you want your categorified versions to satisfy?
So general theorem in categories to satisfy which notion?
Mm-hmm.
I don't get the question, Eugenia, sorry.
So I think this is saying that what are the criteria for this to be successful? What are you
for as a uniform structure to be successful in a category?
Yes, I think possibly this means successful as in good, not just this can be done, but what kind of theorems do you eventually want to prove?
I will answer what I understand without knowing if it's really that's the question. So I need to remind the one asking the question is that on one side, we have these theorems that we prove in a classical settings. For quasi-uniformities, let's talk about completeness, completion, even compactness. And looking at what we know for topologies, many of the classical results on topological spaces have been successfully extended to categories using closure operators. Now, understanding that in classical case, we can move from quasi-uniformities to topologies and back. We want to know these theorems by the side of quasi-uniformities can then also be done on categories, and what do they mean to categories outside the topology? That is a point. I'm not sure if I have answered, but that is a point of our study.
Mm-hmm.
Yeah.
Would the person asking the question like to follow up with anything about that? Well, so
Sorry?
I'll say, are you saying that it's already better understood for closure operators in categories?
Yes, yes.
Mm-hmm.
They are understood. They are understood. And I really need also to mention to him that we haven't even reached the stage of studying properties, as I said in your last slide. We have been describing general behavior, but topological properties, it's now our next step.
So another question, you said it doesn't work so well for interior operators. What goes wrong?
Yeah, this is the main problem. Quasi-uniformity has been closure operator has been very good because it has got many examples outside topology. But the main problem with closure operators, with interior operators, is that you don't find many examples in categories outside topology, which is quite a bad point because you are likely to study notions which remain in topology. They don't go outside. Well, our point is to extend and bring these topological notions even to categories outside topology and see what do they mean by that side. As in fact, the problem with interior operators.
Thank you.
Yeah.
Are there any other questions? No other questions? Well, if there aren't any other questions, let us thank the speaker again. Thank you very much. And we'll now have a little time where we can just have a bit of a chat. And like last time, this is not supposed to be time to pose more mathematical questions to Minani. Minani's now off the hook, but just so that we can have a bit of a chat. And I think that we'll stop the recording and stop the live. Thank you. And perhaps